this particular video, we will be discussing the problem binary tree pre-order traversal. What is the problem asking us to do? We will be given a binary tree. What do you mean by given a binary tree? Given a binary tree means given the root of the binary tree. That is a topmost node, the first level node of the binary tree, so that we can represent the entire tree. We have to return, or you can say print, the pre-order traversal of its nodes values. The all the nodes should be printed in an order known as pre-order. For the tree given, pre-order traversal will be for this tree which you can see, one having left child 2, one having right child 3, two having left child 4, two having right child 5, 4 left child and right child will be null, 5 left child and right child will be null, 3 left child and right child will be null. The traversal will give you the value as 1, 2, 4, 5, 3. 1, 2, 4, 5, 3, the pre-order traversal. So given any kind of binary tree, you should be able to print the pre-order traversal of that specific tree. Let's read the remaining problem statement. We do not have to basically consider the input and output. We have to consider it is already handled by the main method, and we do not have to implement the main method. That is, we do not have to implement the input or output. The inputs, whatever we will get, will be part of arguments, that is parameters. And whatever we have to return, you can consider it as a output. So return the answer according to the return type of the function. That is the number of nodes. All the nodes will actually be stored in a list, or you can say in an array. Now, the structure of the tree is given as a reference to you. It will already be given. You do not have to create a binary tree. And the structure is also what you can't change. You do not have to modify it. You do not have to modify any of the code which is already there. Otherwise, the test cases would fail. Only and only you have to complete this function, binary tree pre-order traversal. So, sorry. So the input format, what will be the input format? We will be given some test cases. Test cases means for different trees or for a single tree, there might be a different number of inputs, or you can say different kinds of trees altogether can be there also. And for each test case, we will be containing n, that is number of trees. So yes, each test case represents different tree. And in each test case, a tree will be given to you using some nomenclature or using some input format, but we do not have to care about it, that how actually tree is constructed from this input. But once the tree is constructed, how will you be able to print the pre-order traversal? That is the main thing. Constraint says the number of test cases can go at max 10 raised per 3. The number of nodes in a particular binary tree can go at max of 10 raised per 5. And all the nodes in the tree will be having values from 0 till 10 raised per 9. Although in the question you are given that all the nodes will be having long value in Java, or you can say in general it is going to be taking 64-bit integral value. So we have to ensure that it is guaranteed that the sum of the nodes, number of nodes actually, for all test cases will be less than equal to 5, 1, 2, 3, 4, 5, 6, 0. That is 5 into 10 raised to power 6. So we do not have to care about test cases, or you can say the constraints right now. The first thing is what approach should we follow? One thing which I said to you that is prerequisite for this problem was recursion. So what we will be doing is we will be solving this problem using recursion only. You can solve it using iteration without recursion, but using iteration will be a very difficult task, at least when we are learning binary trees for the first time. So we will stick to recursion for now. So let's generate a binary tree. Let's create a binary tree which will help us to discuss about all the corner cases possible. What can be the corner cases in a particular binary tree? We can have a node with 2 children. At max 2 children can be there because it is a binary tree. We can also have a node with 1 child, or we can have a node with 0 child. That is a leaf node. So let's say the root node is having 2 children. The left child again is having 2 children. So let me make the 2 children arrows. The left child arrow, the right child arrow. But what we will do is the right child of the root will only have one single child, that will again be the right child. No left child is there. Or we can say the left child is null in that case, null node. And let's do what? For this particular node, we will say there is both left child as well as right child. So there is a left child as well as right child. And for this node, for the right child of the left child of root, we will only have a single left child. No right child is there. So we can say for it, the right child will be null. And for obviously all of these nodes, this one, this one, this one, this one, we can assume all of these nodes children are both null. This is also null, this is also null. Or maybe what we can do is, for this node at least, we can make both the children. That is the left child as well as the right child. So yes, the tree is a little bit large, but I think the traversal will not take that much time. So let's just do a try run for this particular tree only. Let's have the root node with value 10, then 20, then 30. I am giving some random data so that we are able to focus on the traversal and not on the ordering, because in binary tree there is no particular ordering of data. Okay, so for this binary tree, how will I do the pre-order traversal? First of all, what is the meaning of pre-order traversal? The meaning of pre-order traversal is, first, before the root node of any tree, of any subtree, whether the subtree is rooted at 10, it means the entire tree, or whether the subtree is rooted at 20, that is this particular tree, or the subtree rooted at 30, that is this particular tree, or 50 or 90, for any subtree or for any tree rooted at any particular node, the traversal of pre-order will mean that we have to travel all of its left side nodes, that is the nodes in the left children or in the left subtree, before the root node. Left subtree for any root node should be visited before the root node, then root node should be visited, and after root node, all the nodes in the right subtree should be visited. All the nodes in the right side, that is in the right child. But this property should hold true for all the nodes, not only for the overall tree node root, but all the nodes. For 10, for 20, for 40, for 30, every node, this property should hold true. So for all nodes of the tree. But how we are going to ensure that these three steps, or these three you can say these three steps will be required in order to print the pre-order and it will give the correct answer, we can ensure it using recursion. Recursion will help us in order to make the code concise also, and in order to make the ordering according to what we need also. That is, first, what we need a pre-order traversal of the entire tree rooted at 10. So let's say the function is pre-order of root. From pre-order of root, we want the pre-order traversal of left subtree. Left subtree should also be in pre-order. Same goes for right subtree. It is also a tree with different root. So we again need a pre-order traversal, but for the right subtree. What it means? 10 will say what? First, left subtree, give me your pre-order traversal. All the nodes in the left child of root 10. Then again it will say what? It will say 10's right child, give all the nodes in the pre-order traversal. But in between them, I will get printed. And actually, this is not pre-order, this is in order. So what will be pre-order? Pre-order will be the root will be before the left subtree and the right subtree. Then only the left child and the right child will be there. Pre-order means pre, that is before left subtree. So a small mistake, but we have rectified it before the try run. First root node, then left subtree in pre-order, then right subtree in pre-order. Once this is the order which we are able to maintain, we will be able to maintain the pre-order traversal for the entire tree. But actually, how are we making ensure that all the left subtree nodes are in pre-order? By using a recursive call. From pre-order of root, we will make a pre-order of root dot left. We will make a call to the left subtree of the root node, that is to the 20 node. And we will say that we are having faith, we are having, you can say, a kind of expectation from the function of pre-order of root dot left that it will print 20, 40, 70, 80, 50, 90 in the pre-order area, or you can say in the pre-order only. Same for the right subtree. We will call for the pre-order traversal of the root dot right subtree, and before both the left childs and the right child subtrees, we will print ourselves. Not in between left and right, but before left and right. There was some confusion between pre-order and in-order, but root should be printed for the first time, or you can say before any of the children nodes. And this property should repeat for all the nodes. Then the entire recursive function will be recurring for root, root dot left, root, root dot left, root dot right, root, root dot left, root dot right, and so on till the leaf node. But if I will go to leaf node, if we are standing at a leaf node, if I will make a further call, where will I reach? From the leaf node, if leaf node is a root, I will say, yes, print the root dot data. Very good. But are we able to go to the left subtree? No. On left subtree, there is null node. Are we able to go to the right subtree? No. Again, right subtree is null node. So if somehow we are going to reach on a null node, we should not be able to print root.data because null.data does not exist. So actually, before checking the root.data or before printing root's value, we should actually also do what? Check whether root is null or not. So if root is null, then we have to just simply say if root is null, just simply do not do anything, return, just simply return from the function. Then if it is not null, print the root, call for the left subtree, call for the right subtree. Now let's just do what? For the same tree which I have drawn on the left hand side, let's just quickly do a try run. So starting from the root node, what we will be saying, first step, is the root null? No, root is not null, it is having some data. So print the root, okay, 10 is printed. So first output is 10. Go to the left subtree. So make a call to the left subtree. Now for this node's function will stop. It is paused right now. It is not executing because always the function on the top is getting executed because function call stack is there. Stack means the last in first out. The topmost function will always get executed. So this function will get executed. That is, it will also say root is not null, print root. So I am printing 20. That is in the left subtree, print the root node. Then after root node, again make the call to the left subtree for 20. 20 will also say, after printing myself, call for the left subtree. For 40, again, print myself in the first step. Second step, call for the left subtree. For 70, print myself, call for the left subtree. But as soon as I will call for the left subtree, as you can see, it is null. So at null, we are returning. Where we will return? From where we have called. If 70 node is calling null, null will return to 70 node itself. Now what will 70 node do? It had made the call to the left subtree already and it has returned from there. Now it will make a call to the right subtree. But in this case, right subtree is also null. So both of these calls are just going to say return. So I will return back to 70 node. It has done all the three steps. First, it has printed itself. It has made the call to the left. It has made the call to the right. So since all the three steps are done, we will also return because if it is not like if we are going to the last line of the function, it is simply meaning that you have to return from that function. Last line always assumes that you have completed the function and you are just now about to pop the function. So I will pop the function and I will go back to the calling function. If 40 called to 70, 70 will be going back to 40. Once we are reaching back to 40, what is the next line going to be executed? We have already made the left call. Now we will be making the right call. So same thing for 80. 80's first job will be printing itself. So print 80. Second job will be making the call to the left subtree. Nothing is there. Third job will be making the call to the right subtree. Nothing is there. And finally returning to the calling function. So 80 do three things. First, print itself, make the call to left, return, make the call to right, return, because it is a leaf node. Now for 40, finally, can I say that since we have done all the three jobs, printed myself, make the call to left, make the call to right, now is the time to return. Now is the time to pop. From 20, we have made the left call already, but now we will be making right call. Green arrow represents the calling, red arrow means returning. We are having this kind of nomenclature or this kind of visualization. Again, 50 will say, first of all, print itself, then make the left call. 90, print itself, make the left call, nothing is there, make the right call, nothing is there, return. But now see very carefully. For 50, is there any right child? No, right child is null. And if right child is null, we will also return from here. Finally, from 50, we will also return because all the three steps are done. 50 itself was printed. We made the left call, we made the right call, and now we will return. For 20 also, all the three steps are done. We printed 20. We printed all the nodes in the subtree of 20 by using recursion. This was the faith, this was the expectation that 20 will print all the nodes in the pre-order from the left subtree 40, 70, 80, from the right subtree 50, 90. And once all of them are done, we will also return from 20. So what was the expectation by 10? 10 was expecting that as soon as the pre-order is being called on the left subtree, all the nodes in left subtree will get printed, and that is what is happening. Similar job will be happening for the right subtree. So let's just do what? Let's quickly make the call to the right subtrees. So we will call to the right subtree. As soon as I'm going to 30, print 30 in the pre-order or store 30 in the pre-order traversal. Make the call to left, but there is nothing in the left, null, just return. Make the call to right, go to 60, print 60. make a call to the left. First, always left call, then right call. And before of both of these calls, print itself. That's why once we are coming we are doing means first. So first we have to do what? Print or travel. So first traverse 60, then go to left subtree. First traverse 100, both the subtrees will be null. Then go to 110, print, both the subtrees will be null. And now since both the calls are done, we will return. Since both the calls are done, we will return. Since both the calls are done, we will return. And this is the entire output. This is the tree traversal in pre-order using recursion. And the traversal was first root, then left subtree, then right subtree. In order, there will be some other order. In post order again, there will be some other kind of ordering. But let's just do what? We have already discussed the approach, or you can say the milestone number 2 is done. We will now be writing the pseudocode or the instruction manual in milestone 3. But before that, what is the time complexity associated with this particular approach? See, since we are going to each and every node and performing these 3 steps, printing ourselves or storing ourselves in an array which is to be returned is constant amount of time. Making a call to left subtree as well as right subtree is also constant. It means we are going to each and every node only once. We are not going to any node twice or thrice or anything. Every node is being traveled once, but how many nodes are there? N nodes are there. So in total, the time complexity will be order of n. Since going to each and every node is constant, going to n nodes will be order of n. Linear time complexity. What about space? Since we are making recursive calls, we are using recursion. Recursion means recursion call stack space will be there. It means 10 will be pushed into the recursion call stacks. Inside the call stack, let me just make a small call stack. 10 will be pushing 20, 20 will be pushing 40, 40 will be pushing 70. So this is how the recursion call stack will look. Then 70 will pop, then 80 will be pushed, and so on. But in the worst case, what is the number of nodes at max which can be there in the call stack? Whatever is the height of the tree. So in general, we can say it is order of h. But for specific kind of binary trees, which you will learn later on, that is a balanced binary tree, the height will go minimum, you can say log n. So in minimum case, the space complexity will be logarithmic, and the height can go maximum order of n in the case of skewed binary tree. Skewed means all the nodes are in the right side only or in the left side only. Only in one side the nodes are there, kind of a linked list. There is a node, only right child, only left child, only left child, only left child, only right child. So kind of a linear kind of data structure, linked list kind of data structure. So in worst case, space will also be linear. In best case, space will be logarithmic for a balanced tree. But this is best case. It will only be there if the tree is balanced. That is, it has a least height, the minimum height. Height will be log of n. So with that, now let's just do what? Let's just go to the code, not the code, but the code editor and write the instruction manual. First step, which we need is store the root node itself into the traversal. And for that, we are making actually a recursive function. So let's just make a recursive function which will do what? Which will return nothing, which will have void return type. But we will do what? We will pass a root node, whatever subtree we want to print in pre-order. And also we will pass the list which we want to store in the answer. The pre-order traversal will be stored in this list only. That is what we are going to return, the list. Okay, so this function is a recursive function. What is this recursive function going to do? Recursive function is going to basically take root node and the list as parameters and no return type. Nothing as a return type, a void return type function. So let me just write in the bracket void return type. Because we will be just storing the nodes in the list only, no need to return anything. In the first case, what is the first case? We have to store ourselves. The first step is store ourselves. So store roots data. First step is store roots data into the list, in the pre-order list. After storing the roots data, make a recursive call to what? To the left child. Make a recursive call to the roots left child, and recursive call in the sense we have to make a call to pre-order function, pre-order of to root dot left. Similarly, third step will be make a recursive call to the right child, make a recursive call of pre-order function to the right child, to the roots right child. But one corner case we discussed, that was a base case actually. It is known as base case in recursion, which is if somehow root reaches null, if somehow we are going to a null node, we cannot print the null data, we cannot make null dot next or null dot left or right calls. In that case, what you have to do is we have to return. So if before doing anything, before printing data, we have to check if roots is null itself, then we can't do anything, just simply return. And now what we will be doing is be writing the code from the instruction manual, which we have already written, and discuss about the corner cases which can be there. So first of all, from the actual function which was given to us, we have to first of all create a list so that we can return all the nodes data in that list. We have to return the preorder traversal, not just print it. So let's name the list as list, and we will be making it a array list in Java to be precise, because in Java we have a array list as acting as a dynamic array. You can make it as a linked list also, but for now we will be making it as array list. So initially it will be empty. It will get filled once we call the preorder recursive function. So let's just call the preorder recursive function where we will pass the root node and we will pass the list also. That is the answer, or you can say preorder traversal. And once it is going to be filled, we will return it by just simply saying return list. But the one main thing is how we will fill it. We will fill it using recursion. We will be making recursive calls. So first call will be to the right, actually to the left child, not the right. So we will make a call to the left child by passing the same list, and the second call will be to the right child. So preorder of root dot right, and by passing the same list. But before both of these calls, pre-order means first we will print the root data before both the calls. And if we are first printing data, not just print it, but actually we have to store it into the list. So list dot add roots value, roots data we have to add. But if I will run this code, will this code be correct right now? Will it not run into infinite recursion or any kind of runtime error? Let's see. Or any kind of stack overflow exception. Let's see. So it is actually giving me a null pointer exception. The reason is from a null node, if I am going to do null dot val, null dot next, or you can say left, null dot right, we will go to a null pointer exception only, because null, you can't have a value. You have just null, you can't say null dot anything. So before actually doing all of these three steps, we have to ensure that root is not null. If root is null, we can't do anything. We have to just simply return. That is a base case from recursion. So if root is null, return. After handling the base case also, let's just see if we are able to get the output in the order which we expected. So for the sample test case, 5, 1, 4, 3, 6 is working fine. What are the corner cases before actually submitting? One of the corner case might be if there is no nodes in the input tree. That is, let's say there is one test case with 0 node. And if that is a case with 0 nodes, output list should be empty. There will be no nodes in the list because it is 0 nodes in the tree. Yes, it is working fine. Why? Because if root itself is null, just simply return empty array list. But what if there is only one node, and let's say the node is having value 10, and in that case, let's say the 10 node is having left child as also -1. -1 means null according to the input format, and right child also -1. It means it is also null. So there is only one node with root dot data as 10. In that case, the list should also contain 10. So only one node tree should also work fine. Let's see if it is working fine or not. Yes, it is working fine. Only one node in the traversal. So let's now do what? Let's now submit the code to see if it will work for all test cases. And already it has shown me accepted for 18 test cases. And the time complexity, as we have discussed in the approach video, will be linear. Why? Because we will be going to each and every node only once and making these three steps, which are for that node constant in nature, but for n nodes, it will be order of n. And the space complexity, since we are using recursion, we are making recursion call stack space, we are pushing functions in that. Overall, the space complexity will be the height of the binary tree or the depth of the binary tree, which will be at least logarithmic or at max linear. Logarithmic for a balanced tree, linear for a skewed tree. What is a balanced tree? Balanced tree is a tree where the number of levels are minimum. For 7 nodes, this will be a balanced tree. That is only 3 levels, the minimum levels. All the nodes will be at up as possible, as much up as well as possible, as much as possible. But for a skewed tree, it will be a tree which is almost linear. So this is example of skewed tree. 1, 2, 3, 4, 5, 6, 7. That is a kind of linear kind of linked list with just either left child or right child for every node. So in this case, the number of levels or the height of the tree will be logarithmic if you will use some mathematics. In this case, the number of levels will be n only, because at every level there is only one node. So in best case, it will be logarithmic space. In worst case, it will be linear space. Or you can say in general, it is order of the height of the tree, whatever is height. So we have discussed the problem binary tree pre-order traversal, both the approach as well as the code in two parts. What you have to do is you have to code it in your preferred programming language. We will meet in a new video where we will discuss a new problem. And till then, bye bye, take care.